Let's look now at the concept of the inverse matrix. A matrix which can multiply the original matrix to produce the identity matrix. If we have a matrix with n rows and n columns, that is a square matrix, if we have such a matrix A, it turns out that normally we can find another matrix which we'll call A inverse, or A to the power minus 1, which satisfies that A multiplied by A inverse is the same as A inverse multiplied by A, and specifically that those two products equal the identity matrix of order n. So that's the inverse matrix. It satisfies the equations here. Now, if we want to find the inverse matrix, let's start with the smallest case. If we have a 1 by 1 matrix, a matrix with a single element A, the inverse of this matrix is a matrix, again with a single element, 1 over A. So that's the inverse of the matrix with a single element. The next case to look at is the 2 by 2 matrix. Let's take the general matrix with 2 rows and 2 columns, A, B, C, D. Now, if we want to find the inverse of this matrix, what we can do is we can write the matrix D minus B minus C A. That is where we've swapped the positions of the two elements on the main diagonal, and then we've taken the negatives of the two remaining entries, and we multiply this by 1 over the determinant of A. That is, we have 1 over AD minus BC multiplying D minus B minus C A. Of course, this gives rise to one possible problem. What if the determinant AD minus BC is 0? Well, if AD minus BC is 0, we say that the inverse does not exist. We say that we have a singular matrix. Let's see an example. Suppose we're asked to find the inverses of the 3 matrices here. A 1 by 1 matrix and a couple of 2 by 2 matrices. So firstly, let's look at the matrix with a single element equal to 3. This is matrix A, and the inverse here, A inverse, will be again a matrix with a single element, and that single element will be equal to 1/3. So here's matrix A, and here is the inverse matrix, A inverse, or A to the power minus 1. Our matrix B, 2, 4, 6, 11. Well, the first thing we'll do, let's work out the determinant of B. So the determinant of B we can write as the product of the entries on the diagonal. That is 2 times 11 minus the product of the other 2 entries. So we've 22 minus 24. The determinant is equal to minus 2. Well, that enables us to find B inverse. So B inverse, that'll be given by 1 over the determinant of B multiplied by, well, we swap the entries on the diagonal, so 11 here, 2 here. We take the negatives of the two remaining entries, so we'll have -4, -6. We can write it as 1 over -2, 11 -4 -6, 2, or indeed we can write it as -11 over 2, 2, 3, -1. This is our inverse matrix, B inverse. We can check. We might want to write B inverse. Well, here's our B, 2, 4, 6, 11, multiplied by -11 over 2, 2, 3, -1. So when we multiply now, 2 times -11 over 2, that's -11 plus 4 times 3. Bottom left, 6 times -11 over 2 plus 11 times 3. Two times 2, that's 4, minus 4 times 1. 6 times 2 plus 11 times -1. So we get here, putting in the addition and subtraction, -11 plus 12, that's 1. 4 minus 4 is 0. -3 plus 33, that's 0. 12 minus 11 is 1. You can see when we multiply our inverse here, well, we take B inverse, it turns out to be the identity matrix of order 2. We could furthermore check that B inverse B was also equal to 1, 0, 0, 1. Well, one more. Matrix C is equal to 8 minus 4 minus 6, 3. So we start off in the same way. The determinant of C will be 8 times 3 minus -4 times -6. That is 24 minus 24, which is equal to 0. So we see now the determinant of C is 0. If we were to try to work out the inverse, then we'd get a division by 0. We merely conclude that as the determinant of C is equal to 0, C inverse does not exist. What we can say is that C is a singular matrix. It's a square matrix, but there is no inverse.